In this tutorial, I will discuss nutrient removal at the wastewater treatment plant. Nutrient removal is considered a tertiary treatment process in your textbook. It includes both nitrogen and phosphorus removal and is sometimes given the acronym BNR for biological nutrient removal. In this tutorial, I'll go through each of these processes and discuss the different microorganisms that are required to perform these tasks. Nitrogen removal is a biological process that includes both nitrification and denitrification. Both of these processes are required for removal of nitrogen. However, a plant could stop at nitrification. If they do so, they won't remove nitrogen, but they will convert nitrogen from ammonia to nitrate. And this has some benefits because it reduces nitrogenous BOD. For phosphorus removal, a plant can either perform enhanced biological phosphorus removal, which is given an acronym EBPR, or they could choose to perform chemical precipitation. Either of these processes can be used, or a combination of both could be used to reach ultra-low discharge limits of phosphorus. We'll discuss the nitrogen removal first. Nitrogen needs to be removed because wastewater typically has high concentrations of ammonium, around 25 to 45 milligrams per liter as nitrogen. And these are the adverse effects of that ammonia or nitrate if that is converted to nitrate. Ammonia exerts an oxygen demand. Ammonia is toxic to fish. Nitrogen contributes to algal blooms, and the drinking water standard for nitrate is 10 milligrams per liter as nitrogen. Remember that nitrate, if this goes downstream, causes blue baby syndrome, which can ultimately cause death. So the two-step biological process first includes nitrification, and there are actually two different bacteria that need to be selected in the process. First, ammonia needs to be oxidized to nitrite. NO2 is nitrite. And you'll notice here that oxygen is consumed in these reactions. The second step is nitrite oxidation. So the nitrite that was formed from ammonia oxidation continues and forms nitrate. And again, this consumes some oxygen. Now, if you look at this carefully, you start with 1 mole of nitrogen. And in the end, you're left with 1 mole of nitrogen. So we say that nitrification, although it is excellent because it reduces nitrogenous oxygen demand, it actually performs 0 N removal because you start with 1 and you end with 1. This is a pretty fancy microscope picture that was obtained using fluorescent microscopy, and I'm showing this to you because I want to emphasize here you have NOB population, and here you have AOB populations. So nitrification requires a diverse microbial population. One of the aspects or the challenges with nitrification are that these organisms are autotrophic. So recall that autotrophic organisms utilize inorganic carbon. And these type of organisms grow very slowly in comparison to heterotrophic bacteria that remove organic carbon. Because these are slow growers, these organisms require very long SRTs in order to grow in the system. And so if we look here at a range of SRTs, if we simply want to remove soluble carbonaceous BOD, we could have an SRT of 1 to 2 days. This would be fast-growing organisms. But if we want to perform complete nitrification, we need that longer SRT in our system to grow those slow-growing organisms. In this table, I'm showing you some of the impact that nitrification selection has on overall design. And you would get into this in a design class in more detail. So here I have 2 plants. Plant 1 is only doing CBOD removal. And in plant 2, they're performing carbonaceous BOD removal and nitrification. So here you have a difference in SRTs and a difference in HRT. And the HRT has a really big impact on tank volume. Remember that HRT equals volume over flow rate. So because you have a longer HRT, these systems require much larger volume, more than 2 times the volume. This also requires much more oxygen. Because you are also removing carbonaceous BOD and nitrogenous BOD, these systems require more oxygen, and the supply of oxygen costs money. So nitrification, although you don't remove any nitrogen, it does take significant capital and operational cost. If we want to complete nitrogen removal, we first must do nitrification. And this is going to start with ammonia and end with nitrate. The nitrate can then be used to perform denitrification. And denitrification is also a biological process that utilizes anaerobic bacteria that are heterotrophic. So again, these require organic carbon, no oxygen. And in fact, if we want to be very precise, we usually don't say anaerobic, we usually say anoxic, which is a term reserved for bacteria that utilize nitrate but not oxygen. So the nitrate that was performed from nitrification comes in and it's converted in a series of reactions to nitrogen gas. And this escapes to the atmosphere. So when that nitrogen leaves the system, it is removed. So look here, you start with 1 mole of nitrogen and you lose 2 moles of nitrogen in denitrification. So if you're able to perform nitrification and denitrification, you get nitrogen removal. The process of denitrification does have needs. First, there needs to be an anoxic volume or time. That means that there needs to be nitrate, but no oxygen present. It also needs organic carbon because the organisms are heterotrophic bacteria. That organic carbon can come from the influent wastewater, endogenous respiration, which is basically cellular breakdown, or an external carbon source. For instance, some wastewater treatment plants purchase methanol and add it to the denitrification basins. This comes at a price. Next in the module, we're going to discuss phosphorus removal. Phosphorus is typically found in the form of orthophosphate in the wastewater. Phosphorus generally needs to be removed because P is the limiting nutrient for algal growth in freshwater systems, so it prevents algal blooms in the receiving water body. Phosphorus can be removed either biologically or chemically. If biological phosphorus removal is chosen, this is performed by a type of bacteria called a phosphorus accumulating organism, or a PAO. This is a fairly complicated biological step. In the first stage, the cells take up volatile fatty acids, which must be supplied. They store those inside their cells, and as they do that, they release phosphorus. So the phosphorus concentration actually goes up during the process. In the second step, the cells metabolize that stored carbon, and as they do that, they take up phosphorus as polyphosphate. So in this step, the phosphorus concentration in the water decreases. That phosphorus is taken up, the cellular concentration increases. And when the biomass is wasted, the stored polyphosphorus in the biomass is removed. So P removal occurs when sludge is wasted. Again, this is a fairly complicated biological process. In this course, I want you to be aware that there is an organism called a PAO, or phosphorus accumulating organism, that can store phosphorus in the cell, and as we waste biomass, that is wasted. But the detail of the steps here and here is not required for this course. If phosphorus is removed chemically, this is a precipitation reaction, and there are 3 chemicals that are commonly used to precipitate phosphorus. Ferric chloride can be used, in which the ferric combines with phosphate to create the precipitate. Alum can be used, in which you get the aluminum phosphate precipitate, and lime can be used to get that precipitate. Again, these are all fairly common chemicals available and utilized in water treatment that can be applied for chemical removal. The advantages of biological phosphorus removal which is the most common application because it can be the cheapest. The advantages here are that you don't have the chemical cost of a precipitate. You don't produce as much sludge from chemical precipitation. The disadvantages are that you must grow the specialist organisms, the PAOs, and these can be challenging to maintain in the system. Those organisms require an anaerobic-aerobic sequential environment, and so the tank volume increases, and that comes with an infrastructure cost. To summarize this module, nitrogen is removed with two biological processes called nitrification and denitrification. Ammonia goes to nitrite, goes to nitrate in nitrification. In denitrification, nitrate goes to nitrogen gas, and this is where removal occurs. For phosphorus removal, it can be achieved either through biological removal, which utilizes PAOs, or chemical precipitation, or a combination of both. Nitrifiers rely on organisms called AOBs and NOBs, and denitrification requires denitrifying bacteria.